Good morning everyone, this is Abdulaziz Al-Ghamdi. In this video, I would like to present to you a brief overview over the pressurized water reactor. Before we dig deep into the pressurized water reactor, it is important to know what is a nuclear reactor. Then we will talk about the history of PWR and how it works, and then we will go through the main subsystems and the characteristics of PWR. And lastly, we will talk about the advantages and disadvantages. So, what is a nuclear reactor? A nuclear reactor is simply any system or device that is designed so that the nuclear fission chain reaction can proceed in controlled manner. As we know, in a nuclear fission chain reaction, when a uranium-235 atom absorbs a thermal neutron, the nucleus of uranium-235 become unstable and undergo a fission, releasing thermal energy and 3 neutrons, which will be absorbed by other uranium-235 atoms, causing a chain reaction which releases more energy if not controlled. The role of the reactor is to collect and control the amount of released energy. To control a fission chain reaction, we have to control the amount of fission neutron in the reactor. This can be described in terms of multiplication factor, which is the ratio of the number of fission neutrons in one generation to the number of fission neutrons in the preceding generation. If the value of this ratio is greater than 1, then the reactor is in supercritical state, which means the released energy will increase over time. If the ratio is equal to 1, the reactor in critical state and the energy is maintained over time. And if the ratio is less than 1, the reactor is in subcritical state, which means the released energy will decrease over the time. Next, we will talk about the history of pressurized water reactor. Originally designed for US Navy in the 50s to power aircraft carriers and submarines. The shipping port reactor was the first full-scale pressurized water reactor to achieve first criticality on December 2, 1957. However, the pressurized water reactor quickly grew to become most widely used world reactor, with nearly 300 reactors in operation in 2018. As can be seen in this figure, the pressurized water reactor represents 66% of all the reactors worldwide. In the following slide, we will go through the basic operation of pressurized water reactor. In this animated image, which represents a typical design of pressurized water reactor, the following processes occurs. First, the core inside the reactor vessel creates a heat because of the fission chain reaction. Second, the pressurized water in the primary coolant loop carries the heat to the steam generator. Third, inside the steam generator, heat from the primary coolant loop vaporizes the water in a secondary loop, producing steam. Fourth, the steam line directs the steam to the main turbine, causing it to turn the turbine generator, which produces electricity. Last, the steam is exhausted to the condenser, where it is condensed into water. The resulting water is pumped out of the condenser with a series of pumps reheated and pumped back to the steam generator. This figure shows a cross-sectional view of typical pressurized water reactor. As indicated in this figure, water enters the pressure vessel at a temperature of about 290 degrees, follows down around the outside of the core where it serves as a reflector, passes upward through the core where it is heated and then exits from the vessel with a temperature of about 325 degrees. The water in a pressurized water reactor is maintained at a high pressure, approximately 15 megapascal or 2250 psi. At this pressure, the water will not boil, at least not to any great extent. The control rods are inserted into the core and adjusted in order to control the rate of the fission chain reaction. They are capable of absorbing many neutrons. The distance to which they are inserted strongly influences the rate of the chain reaction. The composition of silver, indium, and cadmium alloys are common control rods material for pressurized water reactor. Another main component in a pressurized water reactor is the pressurizer. As shown in the figure, a pressurizer consists of a tank containing steam at the upper section and the water in the lower section, with a pressure actuated spray nozzle at the top and pressure actuated immersion type heaters at the bottom. The device operates in the following way. Suppose that the power output of the turbine is reduced in response to a drop in the electrical load on the planet. This leads to a temporary increase in the average temperature of the reactor coolant and a corresponding increase in coolant volume. The expansion of the coolant raises the water level in the pressurizer, which raises the pressure of the steam and actuates the valves to the spray nozzle. Water from one of the cold legs of the reactor coolant system sprays into the top portion of the pressurizer and condenses some of the steam. This action reduces the pressure and limits the pressure rise. When the electrical load is increased instead, the decrease in coolant volume drops the water level and reduces the pressure in the pressurizer. This causes some of the water to flash to steam, limiting the pressure change. At this time, the drop in the pressure actuates the heater to further limit the pressure reduction. Another key component is the steam generator. Since the water does not boil in the reactor, the steam for the turbines is produced by steam generators, which are heat exchangers with pressurized water on the hot side. A typical steam generator, as shown in the figure, high pressure heated coolant water from the reactor enters at the bottom and passes upward and then downward through several thousand tubes, each in the shape of an inverted U. The outer surfaces of these tubes are in contact with lower pressure and cooler feed water returning from the turbine condenser. Heat transferred from the hot water inside the tubes causes the feed water to boil and produce steam. The steam produced passes upward into a portion of a steam generator known as the steam drum section at about 293 degrees and 750 psi. This gives an overall efficiency of between 32% to 33% for the pressurized water reactor. The fuel in pressurized water reactor is slightly enriched from 2 to 5% uranium-235 in the form of uranium dioxide. Uranium dioxide is a black ceramic material with a high melting point of approximately 2800 degrees. The uranium oxide is in the form of a small cylindrical pellets about 1 centimeter in diameter and 2 centimeter long. The pellets are loaded and packed into sealed stainless steel tubes about 4 meters long. A 1100 megawatt electric pressurized water reactor may contain 193 fuel assemblies composed of over 50,000 fuel rods and some 18 million fuel pellets. The pressurized water reactor uses light water as a coolant and a moderator at the same time. Light water is a good moderator because of its properties in slowing down the speed of the fast neutrons to become thermal neutrons, which are very effective in the fission reaction. The other reason for using the light water is the low cost compared to other materials such as heavy water. Pressurized water reactor fuel of the type described in this presentation is capable of delivering about 30 megawatt day per kilogram of contained uranium before it must be replaced. Where the size of the reactor is an important consideration, as it is in a submarine, highly enriched fuel is used. This fuel enriched to over 90% in uranium-235 and often called fully enriched, makes it possible to reduce the overall dimensions of the core and pressure vessel. Finally, the advantages and disadvantages of pressurized water reactor. The advantages are: first, much fewer control rods are required in the pressurized water reactor. Second, the primary and secondary loops are independent of each other, which make it very easy for the maintenance to inspect the secondary loop components without shutting down the entire planet. Third, the pressurized water reactor has a high power density, which leads to the construction of a very compact core size, which can be used in ships and submarines. Another feature is that the steam used in the turbine is not contaminated with the radioactive material because the secondary and the primary loops are independent of each other. The last feature is that the pressurized water reactor uses light water as a moderator and a coolant, which is very cheap and available. The disadvantages of pressurized water reactor: first, high temperature and pressure in the primary loop, which reduces the safety of the reactor and also increases the cost. Second, the fuel reloading requires planet shutdown, unlike other reactors. Third, the low pressure in the secondary loop, which leads to the low thermodynamic efficiency. Thank you for watching this video and have a nice day.